All right, welcome back. Today, what we're looking at is a circle theorem question. As the question that comes at number 10, then on CXC currently is at number 9. All right, but let us look at this question. So it reads, the diagram below, not drawn to scale, shows a circle with a center O. EBC is a tangent to the circle. All right, and angle OBA is 40 degrees and angle OBF is 35 degrees. So we're seeing the information that they just gave us right here on the diagram we're looking at, all right? So let's go to the first question. So the first question says, calculate giving reasons, all right, given reasons for your answer. The measure of angle EBF, that's a 1 mark, angle EBF. We want to mark that angle, angle EBF, EBF. So this angle is right here. We want to mark that angle right there. So normally I would advise people to mark the angle, have a good look at it before you start doing any calculations. So what are we going to employ now in order to get out this? We are seeing here that this tangent line that we were told about, all right? So we're looking at the tangent line EBC. So we could look at that EBC. So we're looking at this as a tangent line, guys, all right? So that's a tangent line right there. And this OB is a radius. So we're looking at OB as a radius. Remember, though, that there's a rule that says a tangent line meets a radius at 90 degrees at the point of contact. So right here at B is the point of contact. So this is 90 degrees right there. So if that is 90 degrees and we have 35 degrees out of it right here, then the remaining piece, which is what they ask us for here, is simply to say 90 minus 35. And we're definitely looking at 55 degrees right there. So that's a 55 degrees. And normally what I do, I label as I go along. So I'm going to just drop in the label right there. So this piece right here is 55 degrees. What is the reason? The reason, so this is equal to 55 degrees. And we could simply say the radius meets a tangent. So the radius meets a tangent at 90 degrees, right? So the radius meets a tangent at 90 degrees. All right, let's go for the next angle. It says angle BOA. BOA, we want to mark that angle, angle BOA. So let's mark that, angle BOA. Where is that? BOA. So BOA is this angle right here. BOA. Now, when we look at this quickly, there are a number of things that we could do, right? But definitely right now, we're seeing where OB is the radius of the circle and OA is the radius of the circle as well, which means that we have an isosceles triangle. So if we have an isosceles triangle here, and this base angle here is going to equal to this angle over here, which is 40 degrees. So with that knowledge, I can now put together and work out the total internal angle of a triangle. That's 180. So I could say 180 degrees minus the sum of the 40 plus the 40. So it's like 180 minus 80, and that's going to give us 100. So this angle is 100 degrees. BOA is 100 degrees. We saw the isosceles coming in to help us, and then we use total interior angle of a triangle. So we had two reasons there. So quickly, we found out that this is 100. So we're talking about the reason will be one. My first reason was the isosceles triangle right now. So it's the isosceles triangle that gave me the clue. And then secondly, we utilize the total interior angles of a triangle, right? And that adds to 180 degrees. So we're utilizing that, and there it is, we found that. Let's see the next question. And the next question says, angle AFB. Mark the angle AFB. So let's mark that angle. AFB, referring to this angle right there. AFB, all right? AFB. Now we want that angle there at AFB. Now remember, there's a rule that links angle at the center, which would be this right there, to angle at the circumference, which would be that right there. There's a rule that says the angle at the center is 2 times the angle at the circumference. You understand? Providing that they are standing on the same chord, or they're standing on the endpoints of the same chord right there. They're standing here and there, or they're standing on the same chord, same arc, depending on how you want to see. But basically, you're suggesting that they're standing on that, you're standing on that, and then one went to the center here to form that angle, and the other went to the center at F, to the circumference of F. So utilizing that idea, it's going to be half of it, right? So it's half of that, so we could take off these. All right, so we're talking about half of that. So all we'd have to do is to say, okay, 100 divided by 2, and that gives us 50 degrees for this, right? So that's 50 degrees. The quick reason is, as we say, angle at the center is twice the angle at the circumference, all right, providing they are standing on the same chord. And when I say that, I mean standing on the endpoints of the same chord, or it could be the endpoints of the same arc. All right. So basically, it's just a rough idea. All right. The last one says angle OAF. OAF. So angle OAF, let's clear this up a little bit. Clear up these. All right, so we're looking at, so angle OAF is right here, this little piece. There are a number of ways we could get there, but there are a number of ways I could get there, but I'm just gonna go the easiest way right now. Total interior angle of a triangle at 180 degrees. So I could just add up everything, take it from 180 to get this missing piece. I could also utilize, and when I said that, I'm saying, let me just show you what I mean. The total interior, we're saying all of this angle plus all of that angle plus all of this angle should give 180 degrees. So if you notice, we have everything. We have this piece, we have all of this piece, and we have part of this piece. So we could always find that missing piece right there. We could do that. As well as we could say it's going to be 15, as well as we could use the alternate segment principle to understand that this is going to be 55 over here. But we could look at that another time. All right, so I'm just going to suggest that what we could do now, because you're only required to do one. So let me just quickly look at that. We want to say 180 degrees minus the sum of all the other known angles that we have inside right there, 35 plus 40 plus another 40. So if you should put that together, you're talking about 180 degrees minus 50 plus 35 plus 40 plus another 40. And that's 165. As I suggested, it would be 15 because you could see that coming out. All right, so you see that is 15 right there. So some people would have walked it along that way and get their 15. Now, another way, or you could have gotten your 15 is to see this. All right, so another way you could have gotten that as 15 is to see this. So let me clear off some of these. Let's clear off some of these writings. All right. Another way, oh, we could have seen that 15. All right. All right. So we could have seen that 15 another way. Because remember the rule that says an angle between a chord, which is this now, angle between a chord and a tangent. So this is the 55 degrees we're looking at right here. This angle is equal to the angle in the alternate segment, which means all of this is 55. All of this is 55. All of that. So if all of this is 55 and we actually have part of the 55, so we have 40 out of the 55. So all we can do now, or all we also could have done now, is just that we could say this 55, yeah, minus that 40, and we're left with 15 degrees. All right. So we still would have gotten the same 15 from another approach. So depending on how you want to look at it, so you could have used total internal angle in the triangle. So this one is from a total interior, angles in the triangle. All right, 180 total interior angles in the triangle. All right, which is 180. We utilize that to get that out. Or if you use this one, then you could have referred to the alternate segment principle, all right, which is an angle between a chord and a tangent to the circle is equal to the angle in the alternate segment, all right, and we utilize that and then push forward, all right. Thank you very much for watching. Please like, subscribe, and share. Thank you.